Here we are with lesson 4, talking about the rock and roller rinks. We're going to start by looking at the inspection model of how to determine how many solutions there are in an equation. We'll do that by looking at these ones. What we really want to pay attention to when we're talking about analyzing a system of linear equations to decide how many solutions there are is we really want to pay attention to slope-intercept form. Y is equal to m times x plus b. We want to pay attention to two specific things, and that's within the name of the formula, and that's slope and y-intercept. These two things will tell us everything that we need to know about how many solutions our system will have. As we look at problem number 1, we see that both equations are already in this slope-intercept form of y is equal to the slope times x minus, in this case, minus the y-intercept. What we can compare is we recognize that the slope of the first line, m, is equal to 4. The slope of the second line, m, is equal to negative 4. They don't leave us a lot of room, so sorry for a little writing. And what we see is since these slopes are not equal, the only option when slopes are not equal is for the lines to intersect. And because the lines will intersect, this tells me there will be one solution. Now if we look over here to number 2, we see that the second equation is not in slope-intercept form, while the first one is. Y is equal to 4 times x minus 4, or minus 14. So we see the slope is equal to 4, and the y-intercept is equal to minus 14. But this other one, we need to set that up so that we solve for y, to get y all by itself. To do that, we can simply add 4 times x to both sides of the equation, and that simplifies to get y by itself. And then over here, if we're following with the slope-intercept form, we're going to go ahead and put the x coordinate first. So we'll have 4 times x as a positive minus 14. And then I can compare the two equations, and I see that I have a slope of 4 in both of them and a y-intercept that's also equal. When I see a slope that's equal, I know the lines are parallel. When I see a y-intercept that's equal, I know that these are the exact same lines, and we have infinite solutions, meaning that every single point along those two graphs will always be the exact same value. Now on the other side of that, number 3, we see something similar, but we see something different. We see that the slopes are already equal to each other, 4 and 4, but then when we look at these y-intercepts, in the previous one we saw minus 14 for both equations, but now we have a minus 14 and a plus 14. That means that these lines are parallel, and this first one is passing the y-intercept or crossing the y-axis at negative 14, while this other one on the bottom is passing it at positive 14, so much, much higher on the graph. But these two lines have equal slopes and an equal y-intercept, so the b is a minus 14 and the b is a plus 14. So sorry, not equal y-intercepts, but different ones. Equal slopes, different y-intercepts, parallel lines, no solution. Now the last one, we have the first equation in slope-intercept form. The second equation is not solved for y. So let's go ahead and get y by itself. We will add y to this side and then to this side. I'm setting it off to the side a little bit because I need to get rid of that 14 as well. So I'll subtract the 14 and I'll subtract the 14. And then what that sets me up to is this is my expression that it's equal to y. So then we have y is equal to 4x minus 14. And if we just simply bring the y to the other side, 4 times x minus 14, and then I compare this back to the original equation, I see y is equal 4 times x is the same thing, minus 14 minus 14. Again, equal slopes, equal y-intercepts, infinite solutions. There you go. For the rest of this lesson, what we're going to do is we're going to have some scenarios that we're going to analyze and take the opportunity to decide if our best recourse for solving systems of equations is graphing, inspection, like what we did right here, or substitution. And then when will we use those and how do we know what's best? This next problem, we see a situation where the movie tickets at a certain theater cost $8 for evening shows and $5 for matinees. There were a total of 440 tickets sold and $3,130 collected in ticket sales. When we consider each system, we need to determine which system or systems could be used to calculate the number of matinee tickets sold. Explain your reasoning. The first thing that I notice is that I don't know what X and Y represent. I don't know exactly what they represent, but I know what they should represent. I know how much it costs to go to the evening show. I know how much it costs to go to the matinee. The matinee is an afternoon showing, which means before it gets dark outside, and it's a cheaper showing. I know that there were 440 tickets sold and $3,130 collected. So I know that if I just add the two types of tickets together, I should get $440. If I add the money that's earned or that's charged for each ticket, I should get $3,130. As I look at A, I see that that's actually backwards. I see any number of tickets plus any number of tickets equals 3,130 tickets. That can't be right because this is the money, and I see that we've just switched these two around in part A. So A is out. B, if I take any number of tickets and tickets, I get $440. That's accurate. And then I get any number of sales is equal to the money, which is also accurate. So now in this case, I can see that this system will work. What I will have to do is determine what is the value of X and what is the value of Y, and I will clearly define that. So we will say let X be. Now we see 5 is attached to X, so that means $5 for a matinee showing ticket. So that'll be matinee tickets sold. And let Y be evening tickets sold. And in this case, for how would I calculate the number of matinee tickets sold? I would just say solve for, and in this case, since X is matinee tickets, I would solve for X. Okay. On the next one, letter C, looks like they kind of got tricky with us on this one. It's a lot like A, just they switched the X and Y. But this one doesn't work, again, simply because this number is for the money, not for the ticket sales. For letter D, that one's a lot like B, but I see that they've done the same switch right here, but this time it can work. And it can work only if we do this. Let X be evening tickets sold. And the reason for that is because now X is attached to the 8, and we know it's $8 for an evening ticket. And then we can say let Y be matinee tickets sold. And then our final thought with that is if we're figuring out the matinee tickets, then I would suggest that we solve for Y. Now the question that comes out of this, it says consider the valid systems for question 1. So question B, or system B, system D. How would you solve each valid system? Would you choose to solve by graphing or by substitution? And explain your reasoning. When we talk about graphing, here's the dilemma with graphing. In this case, for the first equation, 440 is such a large number that I could have just, in this case, the evening tickets be sold and not sell a single matinee ticket, which means my x-axis needs to extend all the way out to 440, and then my y-axis would have to do the same thing. So that's a really, really big graph. If I don't make it a huge graph, then I have very large intervals that will have to be used in this equation. The same thing can be said for the other equation, only in this one, if I sold just the evening tickets, I would be selling a lot of tickets and making a lot of money, but that a lot of money would amount to somewhere around, X would have to be somewhere around 350 of those tickets. And then if I sold all the X tickets, it would be somewhere around, that total value, 440 tickets, whatever it may be. So the point is that I have really big intervals. So what we look at is we say, in this case, graphing is probably not the way to go. Substitution would be best. And our reasoning is this: since there is a large difference between constants and coefficients. So we mean like this, such large difference between 440 and the ones that are represented here, 8, 5, and then 3 thousandths. There will be a need for large intervals on a graph. Large intervals on a graph leads to less precise measurements at points of intersection. So as we read that, basically what happens is that our two lines will intersect between a couple of grid lines, and then we're left to just rounding to see what we can find as our best version of it.